Now, let us see what an ideal voltmeter is, what an ideal ammeter is. So basically, a voltmeter or an ammeter uses the principle of the PMMC, that is the D-Arsenal moment. An ideal voltmeter is one which can be characterized by its internal resistance is infinite, there is no loading effect, there will be no drift problem, it has an input impedance which is infinite, its fidelity is 100%. Next, its accuracy is high, it has got high precision, high resolution, and no temperature effects. That is, the output will not vary with the effect of the temperature. The different types of errors, the eddy current error, the hysteresis, the stray magnetic field error, the reactance error, etc. all are zero. These are the characteristics of an ideal voltmeter. Now, let us see the characteristics of an ideal ammeter. An ideal ammeter has the internal resistance 0, no loading effects, the fidelity is 100%, high accuracy, high precision, high resolution. As in an ideal voltmeter, here also there are no temperature effects. That is, though the temperatures vary, there is no effect on the readings, and the different types of errors are zero. These are the characteristics of an ideal ammeter and ideal voltmeter. But we can't get an ideal ammeter or an ideal voltmeter. So, this is the circuit of a basic ammeter. This basic ammeter has a resistance in parallel with the meter, which is working on the principle of the D-Arsenal, that is the PMMC instrument. Here, there is a shunt resistance connected across the meter whose value is of very low value, having minimum temperature coefficient. That is, the variations of temperature will not affect the meter. And this resistance Rs, as shown in the figure, is connected in shunt with the ammeter or the meter it is connected in shunt with the D-Arsenal moment. Here, to calculate the value of the resistance Rs, which has to be connected in parallel with the D-Arsenal moment, is because the coil winding in the PMMC instrument is very small and light. It can carry only very small currents. So when large currents are required, it is necessary to connect resistors in parallel. This basic DC ammeter, as shown in the figure, has Rs, that is a shunt resistor connected in shunt with the D-Arsenal moment. So this basic DC ammeter has Rs whose value can be calculated as shown in this slide. Because the Rs is in shunt with the D-Arsenal moment, the voltage across the resistor and voltage across the meter both will be equal. These shunted instruments can be used to measure currents many times greater than their normal full-scale deflection currents by connecting more resistors in shunt. This shunt provides a bypass for the extra current because it is connected across the instrument. So the ratio of the maximum current flowing in the shunt to the full scale deflection current, that is without shunt, is known as the multiplying factor of the shunt. In the equations shown in this slide, we have seen that the voltage across the resistor Rs V shunt is equal to the voltage across the meter, that is Vm. V shunt can be given as Is into Rs. Is is the current flowing through that shunt resistor. Im is the current flowing through the diagonal moment. Even the diagonal moment meter has internal resistance of Rm. Now, Rs can be calculated as Im/Rm by Is. We know that I is the total current, Is is the current through the shunt, Im is the current through the meter. So, Is is nothing but it is equal to the total current I minus the current flowing through the meter I. So, Is is equal to I minus Im. Therefore, Rs can be calculated as equal to Im/Rm divided by I minus Im. So, this DC ammeter can be used to measure very small currents. So, for measuring high range of currents, a shunt resistor is connected as shown in figure. Next, to extend the meter range or to extend the range of this ammeter, we can connect shunt resistors. How to extend the range of the ammeter? The current range of the ammeter can be extended by using shunt resistors. So, if you take one example, let a meter measure a current up to 1 milliamp. If I want to extend its range by 2 times, that is, I want to measure 2 milliamps, we can use the formula Rs equals to Im/Rm by I minus Im. You know the extended range of the meter is 2 milliamps. The original range of the meter is only 1 milliamp. So, if Rm, the meter resistance is 50 ohms, Rs, the resistance to be connected in shunt, can be calculated as already we have seen the formula Im/Rm by I minus Im. It is given as 1 milliamp into 50 ohms divided by 2 minus 1. You will get a 50 ohms. So, if you connect a 50 ohm resistor across the meter, the 1 milliamp range ammeter can be used to measure current up to 2 milliamps. Supposing now, if I want to extend the range to 5 milliamps, then I is 5 milliamps, Rm is 50 ohms, as already we know, Im is 1 milliamp. Now, the shunt resistance to be connected is calculated as already seen Im/Rm by I minus Im. We know Im, we know Rm. I minus Im is now 5 milliamps minus 1 milliamp. So, it gives to 12.5 ohms. Now, if I want to extend the 1 milliamp ammeter to 5 milliamps ammeter, a resistor of 12.5 ohms value must be connected across the meter. This is how you can extend the range of the ammeter to different values. Now, supposing I want a multi-range ammeter, that is of different ranges. As shown in the figure, across the diagonal moment, you can connect number of resistors Ra, Rb, Rc and Rt with a control switch. So, each resistor can be used for one range. Now, supposing I want different ranges of I1, I2, I3, I4. So, the same switch can be used for different ranges depending upon which range I want to use. How to calculate the values of Ra, Rb, Rc and Rt? As already we have seen for the extension of the ammeter, for the multi-range ammeter also, in the same manner, for different ranges, you can calculate the values of these resistors Ra, Rb, Rc and Rt. So if you put the switch in this position as shown, Ra comes in parallel with the meter. If you change the position, Rb may come into position or Rc or Rt depending upon the range of the ammeter which you need. So in the same way as explained, you can calculate the values of Ra, Rb, Rc, Rt. Ra is nothing but Rm by I1 minus Im. I1 is nothing but the current through Ra. Similarly, Rb can be calculated as Rm by I2 minus Im. I2 is the current through Rb. Next, Rc can be calculated as Rm by I3 minus Im, where I3 is the current through Rc, and Rt can be calculated as Rm by I4 minus Im. I4 is nothing but current through the Rt. So you can achieve using a single meter multiple or multi-range ammeter. In this way, you can extend the range of the ammeter. As we know, the current through the ammeter is of very low value. To extend the range of the ammeter, we are connecting the resistors in shunt. These shunt resistors will bypass the extra current which has to be measured. So here we have seen the ideal voltmeter, ideal ammeter, basic ammeter, extension of the range of ammeter and also a multi-range ammeter. At the same time, the precautions which we have to take to connect an ammeter in the circuit is always connect ammeter in series. And also you start the ammeter, if it is a multi-range ammeter, start using the ammeter, first put it in the high range, then you can select the range of the ammeter whichever is required.